Hey everybody, this is Emily. In this video, we're going to learn all about the normal distribution. We're going to talk about z-scores, the empirical rule, and calculating basic probabilities using the normal curve. Before we dive deep into how to use the normal distribution, let's first focus on the shape and characteristics of the normal distribution. As you may know, the normal distribution is bell-shaped. It's symmetrical about a center point where the mean equals the median equals the mode. Now, what exactly does that mean? Well, remember, we can think about a normal distribution as a frequency distribution. So all of our possible values of our variable at hand are going to be placed here on the x-axis. And now the y-axis, or what determines the height of our distribution, is the frequency at which each of these x values occurs. As you can see, the most frequent or common point, which is the mode, occurs here in the center of our symmetric distribution. And this is also the centermost point, by definition, of this distribution, and it is the average point of this distribution. So this point here is where the mean and median and mode all occur. So I'm going to give away the punchline. We use the normal distribution to calculate probabilities by taking the area between the x-axis and underneath the shape of our bell curve. So most of the area happens here in this center portion underneath the curve. And there's only a very small percentage of the area under the curve that occurs here in the tails of the distribution. We use the normal distribution to understand patterns in the population. And as you remember, when we're talking about populations, we talk about parameters. The normal distribution has two key parameters that we need to understand. These are two numerical descriptive measures. First is the population mean, designated by this symbol mu. Again, that mean occurs here at this point, which is the most frequent, the mode, which is the most central point, the median, and it's the average point. It all occurs here at mu in the normal distribution. The normal distribution also has the parameter the standard deviation, designated by this symbol, a lowercase sigma. We use the standard deviation to understand the spread of our distribution, or the distance, how far particular points are away from this central point, mu. It's important to note 100% of all of the scores for this value among the population are included in this distribution. So the entire area underneath the curve and above the x-axis equals 100%. Data is normally distributed in a lot of ways in social science, in other sciences, in naturally occurring phenomena. And often the more data points that you add to a sample, generally the more normally distributed that outcome will become. Now, of course, this is not true when there is a good reason for having skew in your data. For example, think about the number of children that 18 to 24-year-olds have. That's likely to be a number that's skewed right. Remember, shaped like this. It's very uncommon for 18 to 20-year-olds to have children. Maybe they have one or two children, but just because of their age in the life course, it's pretty rare that they would have multiple children when we're thinking at the population level. Some real-world examples of data that is normally distributed includes heights of people, blood pressure, or scores on a test. If you want to have a little bit of fun playing with the normal distribution, check out a Galton Board game. This game lets you see the formation of a normal distribution in action, and I'll put the link in the description. Let's look at one example of the normal distribution in the real world. At the right is a distribution of women's heights who are aged between 30 and 39 years old. These data generally follow the normal distribution, and as you can see, they don't follow it perfectly. In fact, even though many variables conform to a general normal distribution shape, you should expect that most data imperfectly matches the normal distribution. See how it generally maps onto the normal distribution, and yet some points seem to be outliers? That's just fine. As statisticians, we'll make assumptions that the data fits the normal distribution good enough most of the time. Also notice that in this distribution, the values on the x-axis here go from 59 to 72 inches. These are not standardized values. The values are expressed in the original unit of measurement, which is inches. That's perfectly fine. But if we want to ascertain the probability of being above or below a particular height, we'll need to standardize our curve, and we'll go over that in a few minutes. Again, notice that our curve is bell-shaped and generally is symmetrical. Most of our points, most of the values seem to occur between 61 inches and 67 inches. This is where the area under the curve seems greatest. The mean, median, and mode seem to occur right here in the center of the distribution. And then as we move away from the center of the distribution, there's a curtailing of values in the tails of the distribution. The empirical rule is key for us to obtain probabilities using the normal distribution. When data are normally distributed, we can use the empirical rule to describe the percent of data that fall between 1, 2, and 3 standard deviations of the mean. About 68% of the x values lie between -1 standard deviations and +1 standard deviations of the mean mu, which is within 1 standard deviation of the mean. About 95% of the x values lie between -2 standard deviations and +2 standard deviations of the mean mu, or within 2 standard deviations of the mean. And almost all, about 99.7% of the x values, lie between -3 standard deviations and +3 standard deviations of the mean mu, or within 3 standard deviations of the mean. Now again, notice almost all, but not all of the x values lie within 3 standard deviations of the mean. This makes much more sense visually. 68% of the values lie between the points -1 standard deviations and +1 standard deviations above and below the mean, so between these 2 points, and 68% of the entire area underneath the curve occurs between these 2 points. This area between these 2 points and underneath the normal curve accounts for a large portion of this shape. It would be a lot easier if we were working with a circle because everybody's used to working with pie graphs. If I said find about 2/3 of the area of the circle, most of us are pretty comfortable dividing that circle into 3 and then shading in about 2/3 of the data. Here, because the shape under the curve is different, we're finding the center portion that accounts for 68% of the shape, here in the center. If I wanted to find 95% of the values, that again would be pretty easy to estimate looking at a circle and coloring in almost all but not quite all of the area of our circle. Here what we do is we move out another standard deviation away from the mean. So we go to -2 standard deviations below the mean, +2 standard deviations above the mean. We go up to the curve and we shade in the area underneath that curve. You'll still see that there is this area under the curve not shaded in, and this area under the curve not shaded in. But most of the area under the curve is. 95% of the area under the curve occurs between the points -2 standard deviations and +2 standard deviations. We're going to practice a lot more with these numbers, but for now, focus on memorizing these magic numbers. 68% of the values fall within 1 standard deviation above and below the mean. 95% of the values fall within 2 standard deviations above and below the mean. And 99, or even more technically, 99.7%, but not all values, fall within 3 standard deviations above and below the mean. So what is the standard normal distribution? Think of the standard normal distribution as a Rosetta Stone. It allows us to compare between different forms of normally distributed data. In statistics, we often use the standard normal distribution to tell how far a given score is from the population mean. This means that we map our given normal distribution onto the standardized normal curve, where the mean is set to 0 and the x-axis ranges from -3 to +3, and each unit is a standard deviation. So again, look at this normal distribution. Here, mu, the mean, median, and mode point, is set to 110, and then each standard deviation is a set of 20 units. One standard deviation below the mean is 990, another standard deviation below the mean is 970. Now what we do is that we standardize the normal distribution into new units, where each unit is one standard deviation. We accomplish this by calculating z-scores. A standard normal distribution is a normal distribution of standardized values called z-scores. A z-score is measured in units of the standard deviation. A z-score helps us understand distance. It measures how far, measured in standard deviations, that one data point, or raw score, is from the mean. In other words, the z-score tells you how many standard deviation the value x is above, to the right of, or below, to the left of the mean mu. In order to use a z-score, you must know the population mean mu and also the population standard deviation, indicated by a lowercase sigma. We calculate the z-score as follows. Z equals, first you take the difference between your x value and mu, and you divide it by the standard deviation. You're often going to see the formula written this way. Again, your z-score is equal to, first, the difference between x, the data point given to you, minus the population mean mu. Take that value first, and then divide that difference by your standard deviation of the population. Let's go through an example to make sense of all this information. Suppose we know about a population of a particular breed of cat having weights that are normally distributed. Furthermore, suppose that we know the mean of the distribution is 10 pounds and the standard deviation is 2 pounds. Given that information alone, I can draw a normal distribution that represents the distribution of weights of this particular breed of cats. So again, our middle point is mu, and we've been told that mu, the mean of the distribution, is 10 pounds, and the standard deviation is 2 pounds. So one standard deviation above the mean would be 12 pounds. Another standard deviation, again, we are just taking the value of mu, we added 2 pounds to get to one standard deviation above the mean because the standard deviation is 2 pounds. So the value 1 standard deviation above the mean is 12. 2 standard deviations above the mean would be 14. And 3 standard deviations above the mean would be 16 pounds. Let's go in the opposite direction. 1 standard deviation below the mean is 10 minus our standard deviation, which is 8. 2 standard deviations below the mean, so it's negative again. Mu, so it's negative again, is 2 pounds lower, which is 6 pounds. And then a third standard deviation below the mean is another 2 pounds lower, 4 pounds. So now we can understand that most of our cats are going to weigh between 6 and 14 pounds because that would be most of the area under the curve. Let's answer some specific questions by calculating z-scores. So my adorable cat, Punky Brewster, asks us, question 1, what is the z-score for 13 pounds? So first, let's subtract the mean, mu, from our data point, x. We were given 13 pounds, that's our x value, and we want to subtract the mean value. So 13 pounds minus mu, 10 pounds, equals 3 pounds. Step 2, we want to divide this value by the standard deviation. We were told the standard deviation of this distribution was 2. So 3 divided by 2 equals 1.5. That's our z-score. Our z-score is 1.5, or a cat that weighs 13 pounds is 1.5 standard deviations above the average of cats' weights. Because it's a positive z-score and not a negative z-score, we know that it is above the mean, the average of cats' weights. This makes sense. We know that the average cat weight is 10 pounds, and the z-score for 13 pounds should be above it because 13 is larger than 10. Punky Brewster asks us another question. What is the z-score for 6 pounds? Now again, we know that this is probably going to be a negative z-score because 6 pounds is less than 10, or on our number line would be to the left of 10. We subtract the mean from our given data point. Our given data point is 6, so we subtract 10, and we get a negative value, -4. Now we divide this above value by the standard deviation. Our standard deviation was 2, so -4 divided by 2 is -2. Our z-score is -2. Or a cat that weighs 6 pounds is 2 standard deviations below the average cat's weight. And again, this makes sense. We know that 6 pounds is less than our mean value of 10 pounds, so we should see a negative z-score that would be below the average cat's weight. Punky Brewster has one more question for us. How many pounds corresponds to a z-score of 1.25? This question does require a little more algebra than the other questions. Consider the formula Consider our usual formula for a z-score, taking the difference between x and our mean value and dividing it by the standard deviation. Well, we're going to be solving for our x value. We know that z equals 1.25. We know that that's equal to x minus our mean, which is 10, and we're going to divide that by our standard deviation, which is 2. We're going to multiply both sides by 2. 2.5 equals x minus 10. We're going to add 10 to both sides. I'm going to go up here. 10 plus 2.5, x is 12.5. A cat that weighs 12.5 pounds corresponds with the z-score of 1.25. Now let's use the normal curve to calculate probability. Now that we know how to calculate the z-score, we need to know the probability of getting this difference. That is, we want to start learning to find the area under our curve. For example, what is the probability of coming across a cat that weighs 8 pounds or less in our population that we described before? An average weight of 10 pounds and a standard deviation of 2 pounds. So we can use Matt Bogner's probability distribution applet to find these probabilities. This is the long direct link, but for now I've been using a bit link that helps you get there faster, so bookmark this one and memorize it so you can access the app easily. So again, we're trying to figure out the probability of encountering a cat in our population that is 8 pounds or less. As a side note, can we calculate the probability of finding a cat that is exactly 8 pounds? Given the tools we have in this class, no. We find probability by taking the area under the curve, and x equals 8 would be one straight single line up to our curve. In our course, we can't find the area under a single point on a curve. In math, we think that lines don't have any width, so we can't find the area. The probability of encountering a cat that is exactly 8 pounds is 0%. However, we can calculate the area of encountering a cat that is less than 8 pounds. We would be finding the area to the left of x equals 8 to find cats that weigh less or equal to 8 pounds. So first, let's just practice calculating the z-score for our 8-pound cat. We take our given x value, 8, we subtract mu, which is 10, our mean, and we divide that value by 2. That gives us -1, so our z-score is -1. That makes sense because 8 is less than the mean, 10, so we should expect a negative z-score. So we want to find all the area below or to the left of one standard deviation below our mean. Now, let's plug our information into the applet. We know our x value equals 8, our mu value equals 10, and our standard deviation equals 2. And we're going to make sure that the dropdown says p x less than little x, because we're looking for the area under the curve to the left or below our point of interest. When you open up the applet, it's blank, and you enter the values in the given boxes. So here you write mu equals 10, the standard deviation you're given is 2, and you were given your x value, and you enter it here, 8 pounds. Make sure you've selected the right probability calculation from the dropdown, and then click away elsewhere in the box. When you do so, this proportion will show up in the red box, and you'll see the shaded area appear on your normal distribution graph. That applet gives you the probability score in this red box. Thus, our probability of coming across a cat that weighs 8 pounds or less in our population is approximately 1.59, or about 15.9 or 16%. In other words, only 15.9% of cats weigh 8 pounds or less. Or you could say that 84.1% of cats weigh more than 8 pounds. Again, that's because 100% minus the given percentage of cats that weigh less than 8 pounds equals the percent of cats that weigh more than 8 pounds. When we're calculating probability, it doesn't matter whether we're calculating the probability of X being less than a given value or less than or equal to a given value, because we know that there is no probability of X equaling a specific value. All that to say, we now know it's pretty unlikely to find an 8-pound cat or less in this population. Let's try this again. We're going to find the probability of coming across a cat that is less than or equal to 14.5 pounds. Don't need to know anything different. You can already guesstimate that we're going to have the z-score that's positive because 14.5 pounds is greater than mu, our mean. So our z-score is going to be to the right or greater than our mean. We're going to enter our details directly into the applet again. We're going to set x equals to 14.5, mu equals 10 again, and the standard deviation equals 2. When we enter those values here into the boxes at the top, we make sure that, again, we're looking for the probability of being less than 14.5 pounds. Make sure we've selected the drop down with the less than sign, and we click away. We see that the probability is 0.987, or 98.8%. Thus, our probability of coming across a cat that weighs less than or equal to 14.5 pounds in our population is approximately 98.8% of the time. In other words, 98.8% of the cats in this population weigh 14.5 pounds or less. 1.2% of cats weigh more or equal to 14.5 pounds. And we just have calculated that by subtracting our given percentage from 100%. Our top 3 takeaways from this video are as follows. Of course, these are never comprehensive, but it's to make sure we're on the same page. Normal distributions appear frequently in the wild, unless there's a good reason that the distribution should be skewed. I want you to memorize those empirical rule numbers, 68, 95, 99.7. They're going to come in really handy when estimating probabilities. And I also want you to practice using the Bachner applet. All right, everybody. Thanks so much for your help and for tuning in.